I am Dr. J. Glory, Associate Professor of Physics, Institute of Aeronautical Engineering. Today I wish to tell about the classification of magnetic materials. So in this session we are going to cover the topics: introduction about the magnetic materials, diamagnetic materials, that is what are the magnetic materials, diamagnetic materials, paramagnetic materials, ferromagnetic materials, antiferromagnetic materials, and ferrimagnetic materials. Then we are going to see the differences between the main magnetic materials, that is classification of magnetic materials, and then we shall see the reference books or the reference I've seen in this topic. So in this introduction part, so based upon the response of materials in an external field, they are divided into three categories. So which are again it's classified into five groups depending upon the alignment of magnetic moments within the materials. So based upon the response of the materials when it is placed in the external field, and then so that based upon the response of the magnetic materials when placing into the external field, they are divided into three categories, and these three categories are again classified into five groups, important groups, depending upon the alignment of magnetic moments. So these alignment of magnetic moments within the materials. So thus they are known as the five important groups. So which are aligned, which are based upon the alignment of magnetic moments, which we divided into five groups. They are diamagnetic, paramagnetic, ferromagnetic, antiferromagnetic, and ferrimagnetic materials. So based upon the response in an external field, so they are divided into three categories. And again classified or depending upon the alignment of magnetic moments within the material, they are divided into five groups. So these five groups are dia, para, ferro, antiferro, and then ferrimagnetic materials. Okay, let's see one by one. First of all, diamagnetic material. Diamagnetic materials. In this diamagnetic materials, the atoms in the diamagnetic material will have random orientations of magnetic moments. So, in the diamagnetic materials, the atoms have random orientations of magnetic moments when it is in the zero magnetic field, that is in the absence of a magnetic field. Once the magnetic field is applied to the diamagnetic material, all the magnetic moments of its atoms will align in opposite direction of the applied field. So suppose if we apply the magnetic field in this direction, then the magnetic moments of the atoms aligns in the opposite direction to that of applied magnetic field. Okay, So as a result, it exhibits net magnetic moment. It exhibits net magnetic moment in a direction of opposite to the applied field. So it repels the magnetic lines of forces due to the applied field as magnetism is induced opposite to the field. As because of the magnetic moments are aligned opposite direction to that of magnetic field, applied magnetic field, so that the magnetic lines of forces repels to pass through the material. So it repels magnetic lines of forces due to the applied field as magnetism is induced opposite to the field. The relative permeability is mu r is less than 1. Mu r is less than 1. So the intensity of magnetization is negative. Intensity of magnetization is negative, and the susceptibility chi is equals to m by h is also negative. Is also negative. Whereas chi is equals to m by h, m is the magnetization and h is the applied magnetic field. So in this figure, you can see this. These were the atoms, and h is equals to 0 means magnetic field. So the magnetic field, when the magnetic field is equals to 0, and when you are applying some magnetic field in the direction of in any one direction, and the induced that is aligned magnetic moments are in the opposite direction to that of applied magnetic field. We can see clearly here in this picture. So here the applied magnetic field. So applied magnetic field is equals to 0. So you can see here the diamagnetic material when in the absence of a magnetic field H. This figure is related to the diamagnetic material when it is placing in the zero magnetic field. In a zero magnetic field. So here the atoms with the magnetic moments have random orientations. So they are not aligned in any direction, but all the atoms have random orientations of magnetic moments. When the diamagnetic material is placed or in the presence of a magnetic field H, so which is in this direction, which is applied in this direction, the magnetic moments of its atoms are aligned. All the magnetic moments of its atoms aligned opposite to that of applied magnetic field. So the magnetic moments aligned opposite to applied magnetic field H. Okay, so that it repels the magnetic lines of forces. It repels the magnetic lines of forces. So due to the applied magnetic field as magnetism is induced opposite to the field. Coming to the paramagnetic material. In the absence of a magnetic field, all the atoms in the paramagnetic material will have random magnetic moments and do not exhibit net magnetic moment. So when it is placed in the magnetic field, all the magnetic moments due to alignment, due to atoms align into the direction of applied field and exhibit magnetic moment around the field. So as a result, it allows the magnetic lines to pass through it. So here in this diagram, so when in the absence of magnetic field, it has different orientations, different orientations, that is, random orientations of magnetic moments. When there is a when some magnetic field is applied to that of paramagnetic material, so that the magnetic moments of the atoms align along the direction of the applied field. So, because of that, it allows paramagnetic material, allows the magnetic lines to pass through it. The relative permeability mu r is greater than 1. So, where in the case of diamagnetic material, it is less than 1. So, the intensity of magnetization M is positive, and the susceptibility chi is equals to M by H is also positive. Okay. So, here in this diagram, so atoms are having random orientations of magnetic moments in the absence of magnetic field. H is equals to 0. When some magnetic field is applied to the paramagnetic material in this direction, then the magnetic moments of the atoms aligned along the field direction. So all the magnetic moments align in the direction of applied field, so that it allows the magnetic lines of force to pass through it. Coming to the ferromagnetic material. In ferromagnetic material, the magnetic moments are predominantly due to spin magnetic moments of electrons, so which will be aligned parallel to each other to a maximum extent. When magnetic field H is applied, immediately magnetic moments align in its field direction, exhibiting large net magnetic moments along H, so that it allows large number of magnetic lines to pass through it. As because in ferromagnetic material, the magnetic moments are due to the spin of the electrons. So, they are aligned parallel to each other to a maximum extent in the absence of magnetic field. When applying some magnetic field, immediately magnetic moments align in its field direction and exhibits large net magnetic moments along the direction H, so that it allows large number of magnetic lines through the material. So the relative permeability mu r is very greater than 1, and the intensity of magnetization M and the susceptibility chi is equals to M by H are large and positive. In this ferromagnetic material. Here, already up to some extent, the magnetic moments are aligned in the absence of magnetic field, and some magnetic field applied. So all the magnetic moments aligned along field direction. So these are the atoms with magnetic moments. So you can see here, up to some extent, the magnetic moments are aligned in the absence of magnetic field. Okay, so when there is some magnetic field H, so the magnetic moments immediately align along the direction of the field direction. So all the magnetic moments are aligned in the field direction. So the magnetic susceptibility varies with the temperature as per Curie-Weiss law. So the Curie-Weiss law, the susceptibility chi is equals to C by T plus or minus Tc. So where Tc is the Curie temperature. Tc is the Curie temperature. Here we have two cases. That is, chi is equals to C by T plus Tc, and another chi is equals to C by T minus Tc. We have two cases, case 1 and case 2. So when taking case 1, chi is equals to C by T plus Tc, where T is less than Tc, it is high and positive, which correspond to a ferromagnetic material. When T is greater than Tc, that is critical to Curie's temperature. Curie's temperature. So temperature T is greater than Tc is low and positive, which corresponds to paramagnetic material. So if the temperature is less than Tc, then high and positive, so that it relates to the ferromagnetic material. When T is greater than Tc, so it is low and positive, so that it corresponds to paramagnetic material. Coming to the case 2, chi is equals to C by T minus Tc. Where T is less than Tc, it is negative, so it relates to the diamagnetic material. When T is greater than Tc, chi is positive, so it corresponds to either it is paramagnetic material or it may be ferromagnetic material. So the variation of chi with temperature is shown as like this, taking as temperature along x-axis and susceptibility on y-axis. If chi is very large, okay, so that is chi is equals to C by T minus Tc. We can see that here. So this is the critical temperature. Is the critical temperature. So it's gradually decreasing. The susceptibility is gradually decreasing. So, important features of a ferromagnetic material. So, a ferromagnetic material exhibits a spontaneous magnetization. A ferromagnetic material exhibits spontaneous magnetization, that is, even in the absence of magnetic field, it exhibits magnetization. A ferromagnetic material exhibits hysteresis. So these features can be explained based on the Weis molecular field theory, that is domain. According to this domain theory, the material surface consists of small regions known as domains. Within the domain, due to the interaction between the moments, all the magnetic moments will be aligned parallel. In the weak magnetic field, the growth of favorable domain and shrinkage of unfavorable domains takes place. In the high magnetic field, the magnetic moments align parallel to the field. Antiferromagnetic material. So the materials with the anti-parallel magnetic moments, that is the spin magnetic moments, are known as antiferromagnetic materials, and their magnetic moments are shown in this diagram. So anti-parallel, so that is the material with anti-parallel magnetic moments are known as antiferro materials, that is like this. So examples for this is oxides of nickel, chromium, ferrous, etc. Here you can see this in the antiferromagnetic materials, antiferromagnetism. So we can see the Niels temperature. No? So the variation of susceptibility with respect to temperature is given by the Curie-Weiss law. So Curie-Weiss law chi is equals to, from Curie-Weiss law, the susceptibility chi is equals to C by T plus or minus Tc, where C is the Curie constant and Tc is the Curie temperature. From variation with respect to the temperature, chi increases gradually with temperature and attains maximum value at a real temperature and then decreases with increase in temperature. So that's why here in this picture it is clearly shown that the kite is gradually increases to up to some maximum extent, maximum temperature, up to some temperature, then it gradually decreases with respect to the temperature. With respect to the temperature. So the maximum temperature, that is the maximum of susceptibility, the temperature. So where the susceptibility where the susceptibility is maximum, that corresponding temperature is called the needs temperature. So that the susceptibility increases gradually up to the needs temperature, then it decreases with the increase of temperature. Heavy magnetic material. So the substance which consists of anti-parallel magnetic moments of different magnitude. So here anti-parallel magnetic moments. Okay. So the substances which consist of anti-parallel magnetic moments of different magnitude are known as ferrimagnetic substances, and corresponding magnetic moments are shown in this diagram. So the examples for this is ferrites, complex oxides. So the variation of susceptibility with respect to temperature is given by the Curie-Weeks law. K is equals to C by T plus or minus Tc. As we know that C is the Curie constant and Tc is the Curie temperature. And then coming to the classification of magnetic materials, here we are mainly taking as three magnetic materials: diamagnetic material, paramagnetic material, and then ferromagnetic material. Three types of magnetic materials we are taking mainly. So let's see that what are the differences among them. So in diamagnetic material, so it is the property, diamagnetism is the property of the material which has repulsive nature, opposing magnetization. That is, if the field direction is in this direction, applied magnetic field, then alignment of magnetic moments will be in the opposite direction. Okay, that's why a repulsive nature. It has a property of repulsive nature which opposes magnetization. In paramagnetism, it is a property of the material which has weak attractive forces, because initially in the absence of magnetic field, the atoms are in the random orientation of magnetic moments. When there is some magnetic field, then all the atoms magnetic moments are aligned along the field direction, so that it has weak attractive forces. Ferromagnetism. So ferromagnetism, it is the property of magnetic material which has strong attractive forces. As initially, in the absence of magnetic field, the atoms up to some extent they are aligned. They are aligned. The magnetic moments are aligned. When applying some magnetic field, what happens? The alignment of magnetic moments of the atoms immediately align along the field direction, so that it has strong attractive force. The property is due to orbital motion of electrons. Here in diamagnetic material, it is due to the orbital motion of electrons. And in paramagnetic materials, this property arises due to the spin of electrons. In ferromagnetic materials, this property, ferromagnetism, is due to spin of electrons. In diamagnetic material, there is no spin because it arises due to the orbital motion of electrons. Here in paramagnetic material, a spin is random. So spin is randomly. The spin will be a random. So in ferromagnetic materials, spins are parallel. That's why it's showing that strong attractive forces. All the spins are in parallel. So diamagnetic materials are lack of magnetic dipoles. In paramagnetic materials, they have permanent dipoles. In ferromagnetic materials, they have permanent magnetic dipoles. And diamagnetic materials do not possess permanent dipole magnetic moment, so because it is zero permanent. So the dipole magnetic moment is zero. So that spontaneous magnetization is zero in this diamagnetic material. Paramagnetic materials possess a permanent magnetic dipole moment, but there is no spontaneous magnetization in the absence of external field due to the random spin. When coming to the ferromagnetic material, these materials possess permanent magnetic dipole moment also in the absence of magnetic field. So they have spontaneous magnetization even in the absence of external field due to the parallel spin. Here V in is less than V out. So here we can see that it is opposing, that is the magnetic lines of forces. These are the magnetic lines of forces. So they are opposing the magnetic lines of forces to pass through it. So this is the diamagnetic material. So these are the magnetic lines of forces. So this material is opposing the magnetic lines of forces to pass through it. Then when V input is less than. So coming here, so here it is allowing magnetic lines of forces to pass through it. Here also strongly it is allowing the magnetic lines of forces to pass through it and the ferromagnetic materials. The relative permeability mu r is less than 1 in diamagnetic, and in paramagnetic the relative permeability mu r is greater than 1. For ferromagnetic material mu r is very greater than 1. Coming to the susceptibility, in diamagnetic material chi is small, susceptibility is small and it is negative. Paramagnetic materials, it is small and positive. For ferromagnetic material, the susceptibility is large and positive. Large and positive. So when coming to the examples for this diamagnetic materials, we can take copper, iron, zinc, bismuth, etc. Some organic materials. Coming to paramagnetic material, we can take aluminum, so manganese, so copper chloride, like that. We can take alkali and transition metals also for the examples. So ferromagnetic materials, we can take ferrous, ferrites, nickel, cobalt, so like that, zinc. So we have so many examples for this ferromagnetic materials. So these are the classification of magnetic moments, magnetic materials depending upon the magnetic moments, alignment of magnetic moments. So the references which I have given to this topic is engineering physics by K. Tyagarajan, my final publication from Limited, New Delhi, and a textbook of engineering physics written by Anna Bhandu and P.G. Shiv Sagar, and the publication from S. Chandran from New Delhi. So engineering physics by Dr. M. Bhandu, publications Chennai. Engineering physics PK Palaniswamy, publication cited publications Chennai. And then modern engineering physics, Dr. K.J. S. Chandran, S. Chandran, company limited, New Delhi. So these are the reference books I've seen gone through for this topic. So these are about the classification of magnetic materials. Thank you.
Like, share, and subscribe. Hit the bell icon for more updates.